Yeah. Hello students, welcome to IMS GATE Academy. I hope all of you are getting benefited with the foundations course which is being run by IMS GATE Academy. And I hope all of you are attending the sessions which are being taken by Ravi sir and JP sir. So I think Ravi sir is continuing with the computer architecture and organization, and JP sir is continuing with digital circuits. So I hope all of you are attending those sessions. So as I hope also you know that this is a foundation series wherein we will discuss the foundation of every course, wherein you can build up upon those concepts to understand the advanced concepts and then further solve other PYQs also, the PYQs of the GATE also, so that to get the confidence in the GATE examination, right? So after attending these sessions also you'll be able to attend some of the PYQs, but to understand more and more advanced topics you need to keep on further studying to understand the things in a better detail, right? So in these sessions I'll be talking about theory of computation course, in which I will be discussing most of the foundations which are required to build upon the theory of computation subject, and through which you will be able to understand what theory of computation is all about and what kind of questions come in the GATE examination on the subject of theory of computation, right? So I hope, yeah. So I think there is a student, GATE Easy CSE. So what's your good name? So GATE Easy CSE doesn't seem to be the name of the student. So what's your good name? Yeah, good evening. Isaki. Okay, hi Isaki, good evening. Yeah, so Isaki, I think you are also attending the sessions on computer architecture also, and as well as digital circuits, right? Yes, yes. So okay, great. So in this session we will be talking about theory of computation, and I will start with the understanding of theory of computation. So Isaki, what do you think is theory of computation? What is the meaning of the subject? So others viewers can also attempt the questions which I'm asking. It's not only Isaki who will reply. So what do you think is theory of computation? What is the meaning of theory of computation? Yeah. Abstract mathematical model for a physical device. That makes sense. That makes sense. So again, it's quite a good definition. But when you say physical device, Isaki, a physical device can mean anything, right? So there should be something which we cannot call any physical device. Does theory of computation models, hammer? Hammer is a physical device? No, it doesn't, right? So what should be that? What should we say? Right. So you are correct in saying that it is an abstract mathematical model, but we cannot say that it will model a physical device. Any physical device? No, it's not right. Are you understanding my point, Isaki? Yeah. Exactly. Exactly. So when you say digital device, or we should say a computing device, that way it makes more sense. Right, Isaki? So how do we say that? So basically, theory of computation stands for so when I say theory of computation, so TOC, the full form is theory of computation, right? And when I say theory, it means the modeling of the system, right? So it will mean the modeling. So we are trying to model the system, that is basically called theory. So this is basically modeling. And when we say computation, anything, any computing device which we can model, any computing device which we can model. So is basically studied in theory of computation. So what we are trying to do is we are trying to model the behavior of any computation device. Is it making sense? Right? So what we are trying to do is, so for example, any computing device is there, it would have a large piece of code. How would we model its behavior? So to model that behavior, we have to study the subject of theory of computation, wherein making the models makes it easier to understand what is exactly going on, right? So this is what is the basic motivation, what is the basic meaning of the subject of theory of computation is, right? So is it okay? Making sense? Yeah. So and when I'm trying to introduce the subject, let me tell you how we are going to plan it. So we will be covering, we will be meeting for almost 10 days from 4 p.m. to 5:30 p.m. to discuss theory of computation, and all these sessions will be, all the foundation course sessions will be coming up on the IMS GATE Academy YouTube channel, right? So you can come directly to the IMS GATE Academy YouTube channel. You can even like and subscribe it so as to get the notifications on time. So I'll be giving the detailed schedule at the end of this session about what are we going to cover in all these 10 sessions. But in general, all these sessions will be from 4 p.m. to 5:30 p.m. and all these sessions will happen on the IMS GATE Academy YouTube channel, right? So so let's proceed further. So that's all about, that is basically the meaning of the subject. What we are trying to do is we are trying to model the behavior of the computing system so as to understand what exactly is done by the device, what is the behavior of that device. That is basically theory of computation, right? So when I say model the behavior, so how will it help me? It will help me in understanding the limitations of that device. It will help me in understanding the capabilities of that device. What do I mean by that? That I will be able to understand what exactly that device do, what is exactly that device can do, what is exactly that device cannot do. So that is what we are trying to study in the subject of theory of computation, right? So let us try to understand what are the various applications of theory of computation are, and on that we will definitely build further. So what do you guys think are basically the applications of theory of computation, where it is exactly going to be used? How will it help me? What do you guys think? Yes, any answers? Where it will use? Once I have modeled the system, how will it help me to build further things? What will be the basic benefit of that? Any ideas? No ideas? At least maybe you can throw some junk words so that I can try to relate them. Okay. So Isaki has 2 points. He says designing the sequential circuit. Designing the circuits, I don't see that's a direct application of theory of computation. Designing the compiler design, so designing the compiler, it should be designing the compiler. So that does make sense. So basically it will help us in designing the compiler, that is for sure. But before that, we should understand what is the exact application. Compiler design is an extended application of theory of computation. Let's try to understand that. So basically what do we have is, so what is the problem? So basically we have languages, right, with us, and we have to check that whether the given string that I'm giving to you at runtime, it belongs to the language or it does not belongs to the language. So for example, what you can take is, for example, let's take an analogy from the English language. We know English is a language. There are sentences in the English language, and we have to tell that whether a given sentence belongs to the English language or not, right? So that is a challenge, right? So similarly, when we come to the domain of computers, what we will have programming languages, right? So for example, given a programming language called C, say for example, C is a programming language, right? And I have to tell whether the given program that I have given you is a valid program or not, right? So whether the program that I have given you is a valid program or not. And are you understanding the scale of the problem? It is just like analogous to the English language. We have an English language, and there are lot many words in the language, right? And through those words, I can make multiple strings in the language. And I have to tell at runtime whether the given string, whether the given English sentence is making some sense or not. Is it a valid sentence or not? Similar to that, the problem over here is the given C program that you have written is basically a string of characters, right? So for example, any C program if you take, for example, I have a C program which prints, say, hello world, right? So if I take this program which prints hello world, right? Let us take this program. Now I have to check at runtime that whether this sentence, whether this program that I have written is a valid C program or not, which follows the semantics or the syntax of the C programming language. Whether it has a meaning or not, whether it follows the rules of the C programming language or not. So that is the problem which we are trying to deal with. So can you tell me, is it possible that I store all the C programs that I have in this world in the computer system, and then at runtime check that whether the string, whether the C program, the string in this case is your C program, the string in this case is your, the string over here in this case is your C program. So can you tell me, will it be a viable method that I store all the programs in this world and then at runtime ask you this question that whether the program that you have written is a valid program or not? Is it possible or not? Is the question making sense to everyone? So what I am trying to ask you, that is it possible that I store all the valid programs in this world in the computer system, and then I ask at runtime that whether that program is making some sense or not? Is it a valid program or not? Is it possible to do that? Isaki, what do you think? Is it possible to do that? Answers, at least yes, no, something you should say. What do you think? No. So what could be the reason why we can't do this? You said no. What could be the reason why we cannot do this? What is the problem? Okay, don't know the problem. Okay, so anyways, let me try to answer. So understand this point. Can you tell me how many C programs exist in this world? It is as good as asking you the question that how many English sentences exist in this world. Is it possible to answer this question? Can you tell me a count? Isaki, do you understand this point? We do not know the count. We know that there are infinite number of sentences that exist in this world. Similarly, infinite number of programs exist in this world. Exactly. You're correct. They are infinite. And it is not possible to store an infinite thing into our finite hard disks or any disk you take. Even if you take a petabytes of memory, terabytes of memory, gigabytes of memory, anything. Petabytes is the highest unit. Even exabytes of memory if you take, you cannot do that because it's an infinite thing. And even if you find something which will be able to store all the valid C programs in this world, you will not be able to search them. Which search you will apply? How will you sort them? Even if you sort them, it will not make any sense to apply binary search over there. How would you sort? What will be your sorting parameter? Even if you take the linear search, it will take infinite amount of time. Since the number of strings are infinite, it will take infinite amount of time for you to check all those strings. It will not make any sense. Are you getting the point? So you cannot store all the things in the memory and then try to understand that whether the given string that I have given to you at runtime, the program in this case is a valid C program or not, is a valid string or not as per the syntax rules of the C programming languages, right? So again, just to summarize all this discussion in one line, I cannot do this since the things are infinite. Even if I find some method to store it, I do not have anything, so that I do not have anything to search even. So for example, first of all, storing it is a problem. And if somehow you are able to store it, you will not be able to search it, right? Does this give enough motivation? So we understood that we have to model the behavior of the computer system, but how will it help? Why the modeling will help? Because we cannot store the things in the finite memory of the computer system. We have to have some representation which should be finite, which should be able to tell me that whether the program that I have given to you at runtime is a valid C program or not. So let's try to understand this in a better way. So for example, let's understand this. So for example, you need to have some representation. You need to have some representation to which you give any string at runtime, right, which should be able to tell you if it belongs. So this representation, what is this representation? This representation is going to represent your language. So this representation represents your language. This represents your language, right? So you have the string, you need to have a finite representation of the language. So you have a language with you, and you have the string with you. Now the question is whether the given string belongs to the language or not. That's what the question is, right? Now if I directly apply this string over this language, I do not have any finite representation of the language. I cannot store all the strings in the language. So what I can do is, I will have a finite representation of that language, and when I give a string to that representation, what will happen is, if the string belongs to the language, it will say yes. And if the string does not belong to the language, it will say no, right? And this language can be any language. It can be your English language, or it can be a very finite language. Say for example, a language can be set of all strings starting with A, set of all strings of length 2, set of all strings of length 4. Anything can be a language. This can be as big as an English language or a C programming language, or this can be as small as saying that set of all strings of length 2 or length 3 or 4 and so on and so forth, right? Now, imitating it for the programming languages, what will be the representation? I would say that this represent again. So just to add one more point over here, just a second. Yeah. So what is this representation? Yeah, Isaki, can you tell me what is this representation? What is this representation called? Anyone? Others who are also there in the session can also reply. What do you think? What is this representation called in terms of theory of computation? This representation is exactly your model. But what is a better name for this? What is the name which is most commonly used for this representation? Oh, this is exactly the model. But this model in terms of theory of computation, we call it as automata, right? So this model is basically your automata, which will represent a language, right? And when we give it a string, it will tell you that whether the string belongs to the language or it does not belong to the language, right? So this model is an acceptor of that language. This model, this automata, is basically the acceptor of the language. If the string belongs to the language, it will say yes, it belongs to the language. If the string does not belong to the language, it will say it does not belong to the language, right? So does that make sense? Yeah. So now let us try to map the same thing. Let us try to map this to a programming language. So your string in case of programming language, your string in case of programming language, your string in case of programming language will become your C program. Your string in case of programming language will become your C program. And what is this language? This language becomes your C programming language. This will become your C programming language. And the automata, for example, if you are doing the syntax analysis part, when you are doing the syntax analysis part, this automata will be a push down automata. Why it is push down automata? Why not any other automata? All this is an advanced discussion which we'll do over a period of time. We cannot do all this discussion in one lecture. Otherwise, this lecture itself will become everything, right? So we are just trying to introduce the subject a bit, right? So I hope this is clear to this point. Maybe you guys can confirm me if I'm asking whether it is making sense or not. You may say yes or no. In case there is a doubt, you can say no. In case everything is clear, you can say yes, right? So this makes sense till this point. So what we did is we tried to understand what is an application of theory of computation, right? So now, once you have understood this is just one application, there can be multiple applications also. So let us try to understand other applications also. I'll just motivate the application. I will try to motivate I'm just trying to motivate the applications of theory of computation. One application is, as I said, accepting a language, right? So as I said, so when I say accepting a language, given a string in the language, you have to tell me that whether the string belongs to the language or not, right? Right? And then another application could be compiler design, as you rightly said, Isaki. So what is another application? So compiler design, in case of compiler design, your string becomes your C program, and then your language becomes your C programming language, and through that you can tell whether the program that you have written is a valid C program or not, right? So that is basically the second application. And then comes, as I said, to understand the capability of a machine, right? When I say to understand the capability of a machine, so when I say capability, that is basically understanding what is it that a machine can do and what is it a machine cannot do. So basically to understand the limitations of the machine as well as the power of a machine, that what is it it can do and what is it it cannot do. And this basically when I say power, this machine is basically your model. This machine is your model, and this when I say machine, this is your model as well as this is your automata when I'm discussing all this, right? I hope this makes sense, right? So this is basically, these are the basic three applications we discussed. Then other applications, if I say, it is basically used in verification, right? So Isaki, any ideas about verification? What does a verification mean? What does it mean? What does it mean? What do you mean by the term verification? Can you tell me? So if I'm saying that this is an application, this is basically an application of theory of computation, can you tell me what is verification? Any ideas, like any ideas you can give me? What does the term verification mean? Any ideas? I think you must have listened the word testing. Is verification and testing are the same things? What do you think? Is it same or different? Any ideas will help me. But if you don't have no idea, then tell me no idea, then maybe I'll answer it. But what do you think? What is the difference between verification and testing? What do you think? Achha. So Isaki says forgot, no idea. Again, so let me try to answer it. When you are testing a system, you are trying to find out so when I say testing, testing is an attempt to, it is an attempt to find errors in the system. It is an attempt to find errors in the system. And verification is to prove that the system meets its requirements. Right? Now, what is the difference? So basically what you are trying to do is, when you are doing the testing, you are trying to find out errors in the system. If you have done testing for say n number of hours, you can say that in these n number of hours I could not find error in the system, but you still cannot claim that your system is error free. If you have to prove your system is error free, you have to prove that the system meets its requirements. So that means that if the system meets all of its requirements, then we can claim that the system is error free, right? So whatever are the requirements of the system, if you are meeting all those requirements, then you can definitely claim that your system is error free. So how do we do verification? How do we do verification? So we are trying to do, we will model the system, we will model the entire program using an automata model, and through that we will ensure that the program does what it is intended to do. If the program does exactly what it is intended to do, then we say that we have verified the system, and then we can say that yes, my system has been verified, and I can say that my system is error free, right? So verification is checking the system, proving that. So basically it's just like a mathematical proof that you will give for your system to say that your system is an error free system. I hope you understand this point, right? So what you're trying to do is, you are trying to prove that your system is error free. So it's just like a mathematical proof. Testing is just like you are randomly trying, maybe through an approach you are trying to make some test cases, and through that you are trying to test that whether my system is giving the right output or not, but still you cannot prove that yes, my system is 100% correct. This you cannot prove until you mathematically model your system using some automata model, right? And there are some other automata models which are used to model the behaviors of the programs, which you will study in your advanced studies, like Bookie automata and so on and so forth. This and the temporal logic also you will study later. That's not the part of the GATE syllabus. This is basically an advanced application of theory of computation, right? So just to give you an example, like for example, one of the examples is, I hope you know about the system called Ariane 5. Right? I hope you know about Ariane 5. So any ideas about Ariane 5? So you can say no idea. If you do not know, I'll tell it, but at least if you know, I'll be happy to know. Any ideas if you know about Ariane 5? No, you don't know. Okay, no issues. So basically this is a project wherein multiple nations gathered to launch GPS navigation system. They wanted to launch multiple satellites, and the navigation system which we got somewhere in 2010, somewhere around this the second decade of this century, the navigation became popular in this century, in this second decade of the century. If Ariane 5 would have been successful, we would have got the navigation system 10 years ahead, right? So what was that system? So multiple nations were trying to put satellites in the orbit so that the entire Earth can be mapped and we can get a better navigation. But what happened is lot of money was invested in this to get this done. But once the satellites were launched, once the rocket was launched, all the system was burnt in the air, and all the entire money was wasted. So what was the problem? What is the problem? How I am trying to relate that problem with the theory of computation. So the problem over there was they just tested the system, they did not verify the system, and the problem was that was existing there was the floating point conversion was not accurate. The floating point conversion of the velocity was not accurate, right? So if they would have verified the system, then such kind of errors could have been prevented, right? So in verification, you will model the behavior of the program using some model, and then you will apply some logic system to prove that your system's behavior is exactly what you want, right? So this is how basically we understand that verification is much more powerful than testing, and theory of computation directly finds its roots, theory of computation directly finds its applications, I should say, in the topic of verification, right? Right? Does it make sense? Isaki, is it making sense to you? And if you talk about any multi-billion, the giants, the tech giants, for example, Facebook, yeah. So any tech giant you talk about. So for example, you talk about Amazon, you talk about Facebook, you talk about Microsoft, you talk about Google. All of them are investing a lot of money in verification. It's not that they are just doing testing, because doing testing is just not sufficient. You require to verify, you require to ensure that your system is error-free. And what is the way to go? You model your system and then you verify its behavior, right? So that is how. And so once you enter into your dream colleges for doing the MTechs, you will find subjects on verification, wherein you will see, you yourself will verify the systems, right? In my MTech days, I verified the code on the snake code, the snake game code that is there on the Nokia systems. I verified that code and found that there were bugs in that code also, right? So so just to give you a quick sneak into that. So for example, so what do you guys think? I think so Isaki, what do you think? So for example, in the snake game that we used to have in the Nokia mobiles that we used to have earlier, so what used to be there? So the snake will keep on eating the food that is there on the way, and then it will keep on growing in length, right? And at the end of it, if for example the snake hits himself or herself, let's say, then in that case the game will be over, right? That's the game roughly. And now so what I thought is, what would be the case in case the entire snake fills the space, for example, and there is no space left to fill the food, to put the food? What should happen? You understood the problem? So for example, you have the snake game with you. In that game, the snake is going to eat the food which is there on the way, and it will kill itself if it hits itself, right? But there may be a case when you fill the entire space, there is no place to put the food. What should happen? Ideally, it should say win. Or what do you guys think? Is the question making sense to you? Isaki and I think Vasudha is also there. What do you think? Is the question making sense to you or not? So what should happen in case the snake game fills the entire space, right? So what should happen is, it should say that you have won the game. There is no place where I can put the food. It should not say that you are killed, right? But what happens exactly in the system, we verified this on, so this was a project in one of the courses on specification and verification of programs that I did at IIT Bombay. So there what we did is we used the system called, it should say game over or it should say you have won, right? So Isaki, either it should say game is over, But I feel that it will be a, it will be a bad thing to say that, the game is over. Why? Because the program has failed to give me the food. Why I should say game is over? I should say that you have won the game. You go to the next level, right? So I feel that it's something like this should happen. But even if it says game over, even I am fine with that also. But to our surprise, it says it goes into an infinite loop. What is an infinite? Why infinite loop? It will find out an empty space using out of the given empty spaces. What the program was doing, it was out of all the empty spaces, randomly it was picking up one empty space to put the food. But since the program had no empty space, since the situation had no empty space, it went into an infinite loop to find out an empty space. So to our surprise, what happened is, instead of either saying you win, instead of either say or saying that the game is over, it ends up saying that, you are, it ends up going into an infinite loop and the program gets stuck, right? So such is the impact of verification. Through verification, you can find out such errors. Just by doing testing, you cannot prove that your system is 100% correct, right? So I hope this motivates you enough to understand the applications of theory of computation, and it motivates you enough to study the subject of theory of computation. So clearing gate is one motivation that is clear to all of us, but to understand the real implications of the subject, it's also very important, right? So Vasudha and Isaki, does it make sense to both of you? Yes or no? Right? Okay. So let's go further. So other applications, like you go to any system, any digital system that you see, as Isaki rightly pointed out, the vendor machine, the elevators, the automatic traffic signals, all of them are using some program at the back end, and that can be modeled through an automata, right? And then similarly, the computer system itself, it goes from one state to another state. It goes from, you know the processes, right? You know the processes goes from one state to another state, the ready state, the run state, the IO state, the blocking state, or the running state, or maybe the terminating state, right? So all these states basically can be represented. A computer system can be also be modeled using an automata. Similarly, the network protocol stacks or the microprocessors, all of this can be modeled using an automata, and then we can verify their behavior, right? So yeah, so that's all is basically to understand what the subject is, what are its applications, and to understand its motivation, and then let us start understanding the concepts in the subject, right? So that's all about the introduction to some extent. Let's try to understand the terminology that is involved in the subject, right? So first thing that comes are basically the symbols. So symbols, so we should first understand what are symbols, right? So it says that, I think the definition is already written, that the smallest building block including numbers, alphabets and characters is basically the symbol, right? So so if I talk about any any smallest unit, so for example, it can be numbers. So for example, 0, 1, 2, 3, 4, 5, any number. Then alphabets, A, B, C, D, anything can be your symbol till Z, or if it is in any other language, it can be any other symbol also, right? And then when I say characters, any character can also be a part of the symbol. So for example, @ hash, or I should say any other underscore, right? So, or the dollar maybe, right? So anything can be a symbol, right? So now so when I say so it's not just that the symbols that we have in the computer system are only the symbols. It can be just anything, any damn thing. So for example, the Hindi alphabet, so the Hindi literals that we have, like for example, they are also part of, they can also be called symbols, right? So, and maybe anything. So for example, if I want to represent a system where I want to represent boys, I can make this to represent them. This is also a symbol, right? The girls should not feel that they are not represented. Let me represent girls also, right? So this is also a symbol, right? Is it making sense? So anything, the smallest building block of your system is basically going to be your symbol, right? Now let's talk about the next thing, alphabet. What do you guys think is alphabet? So this is basically your symbol. Now what is an alphabet? Alphabet will be a finite set of symbols. It is represented by using, it is a finite set of symbols, and it is basically represented by sigma. So any finite set of symbols is basically called, so Vasudha has a question, symbols can have combinations too? No. Combinations we will consider when we are discussing the concept of strings. Symbol is the smallest building block. So any string you take, what is the smallest unit in that? That will be your symbol. Is it making sense, Vasudha? Yes or no? Yeah. So now when I'm talking about alphabets, alphabet is a finite set of symbols which you are going to use in your language. So can you tell me if I ask you this question, what is the alphabet? What is the alphabet for the binary language? What is your sigma for binary language? What is your sigma for binary language? Can you guys tell me? Zero and 1, very good. So your sigma for binary language is 0 and 1. For decimal system, your sigma will be 0, 1 up to 9. And so on. For hexadecimal system, you will have A, B, C, D, E, F also. For octal system, you will have some 8 symbols from 0 to 7, right? So that is how your alphabet is defined. Can you tell me the symbols for English language? What is sigma for English language? What is sigma for English language? Can you tell me? What will be sigma for English language? Can you guys tell me? Your alphabets, A to Z, that will be your sigma, right? This is your sigma for English language, right? Exactly. The capital systems also, right? Agree to your point, Isaki. Even the capital letters also will also be part of it, right? All these are the part of the English language. Now let's come back to computer science. What do you think? Sigma for C programming language. Can you tell me the sigma for C programming language? Can you tell me the sigma for C programming language? What will be the sigma for C programming language? What will be the sigma for C programming language, guys? Vasudha says, so we do not consider ASCII values. For maths, it is sum. Yes, so for maths, your sigma will be, right, very good question. So again, you have to define when you are saying maths, Isaki, you will have to tell me what are the various operations that are allowed in your math, right? For example, you have a math which only has 2 operations allowed, that is subtraction and minus, subtraction and addition. So your sigma will become the 9 digits and then plus and minus. Make sense? So Vasudha, I am just trying to understand your question. You are saying, so we do not consider ASCII values. So ASCII values for English language? No. But for ASCII values for C programming language? Yes. you are 100% correct. Does it make sense, Vasudha and Isaki? Could I answer both of your questions? Like questions asked by each one of you? Is it okay? Yeah. So when I say C programming language, all the ASCII values, all the ASCII characters will come in my sigma. And I hope you are now realizing using these ASCII characters, I will be producing my C program, right? I will get back to that point again, don't worry, right? So now what is the next thing? Once you have alphabets, through these alphabets, what you are going to build? You are going to build strings, right? Through these alphabets, you are going to build strings. And what is a string? It is sequence or combination. It is sequence or combination of some symbols from a given sigma, right? So for example, if I talk about any any sentence, if I talk about any sentence in English language, so let's say this is a foundation class, right? So if you see, this is a string which has been formed. Even in the English language, what you can also add is the space. The space is also a part of the English language. Not even this, you can also add the punctuation marks. That will also be your symbols. Alphabet in the English language, punctuation marks. I hope you know what are punctuation marks: the comma, the exclamation mark, the full stop, and so on and so forth, the semicolon, and so on and so forth. They will also be added. The space will also be added, right? Yes, making sense to both of you? Okay, so now let's try to go here. So this sentence that I have made using the combination of the alphabets that I have, I got the strings in the language. So for example, these are all individual units, the space, I, S, space, A, space, and so on and so forth. So these alphabets have been used to form the strings in the language, right? Right. So, so this is one thing. And now when I say strings in the C programming language, your strings will be your C programs. And when I talk about, so for example, let us take certain examples. So like for example, if I define my sigma as AB, if my sigma is A comma B, so what will be the strings? I can make any string, maybe A, single A, double A, ABA, BB, BBA, ABAB, everything is a string, right? So what I'm trying to say is, you are trying to form a combination or a sequence of alphabet to form strings. I hope the definition of strings is clear. So what do you guys think? Once you have understood strings, what could be the language? What could be the definition of language? So what is a language? So you know the definition of symbols, you know the definition of alphabet, you know the definition of strings. Now what do you guys think can be your string? What do you guys think can be your string? Sorry, what do you guys think can be your language? Answers, guys. What do you think can be your language? So combination of not combination of strings, Vasudha is right to some extent, saying that the combination of strings, combination word is wrong, and Isaki is telling me set of statements, not up to the mark. Now you are correct, 100% correct. Set of strings is basically your language, right? So, and on the top of it, set of strings over sigma which are bound by some rule. So, given an alpha, given a sigma, that is alphabet, I can make infinite strings. Right? Using sigma equals to AB, I can make infinite strings. But when I say a language, I have to tell you what kind of strings. So that becomes your language. So what is language? Set of strings which are bound by certain rules becomes your language, right? So when I say C programming language, I can write any damn C program. So when I'm writing my C code, I can write any damn code which might not even work. So what is C programming language? It is a collection of the valid C programs which are bound by certain rules, right? So one of the rules is, for example, the declaration should precede the usage. For example, integer a should come first and then I can use a. This is a rule of the C programming language. This is a semantic rule, right? In the subject of compiler design, we understand what are semantic rules, what are syntactic rules. We'll see that. But now, when I am saying the language L, I will be talking about some rule through which I will bound the strings in the language. And even after binding, the language can still be finite or infinite. We'll see through an example, right? So let me redefine it. Set of some strings over sigma bounded by some rule is basically your language, right? Now let's try to see this example. Set of all strings of length 2 over sigma equals to AB. Can you guys tell me what is this language? Can you tell me what L1 will contain? What will L1 contain? Can you write down and list down this language? Can you please write down and list this language? Very good, Isaki. So what we are trying to do is, we know our sigma is a comma b. What is your sigma? Sigma is telling us the smallest possible symbol that is there in my language is basically a comma b. Now I can make infinite strings out of a comma b. I said that I have to include all the strings of length 2 over sigma equals to a comma b. So when I say all the strings of length 2 over sigma equals to a comma b, I can write it as AA, AB, BA and BB. So this becomes my language. So out of the infinite strings, I have bounded them by some rule. What you get after is a language. After applying some rule on the strings that can be generated using a sigma, what you get after that is basically a language, right? Then what is L2? Set of all strings of length 3 over sigma equals to a comma b. So what will be L2? All the strings of length 3. So for example, L2 will be AAA, AAB, ABA, ABB, BAA, BAB, BBA and BBB. Right? So this becomes your language. So can you tell me both these languages are finite or infinite? What do you think? These are finite languages or infinite languages? What do you guys think? Finite languages. So does that mean that every language will be finite? Does that mean that every language will be finite? No, right? I know English language, it is infinite. I know C programming language, it is infinite, right? So let us see an example. So what I am trying to say is, even if you put some rule, even then your language can still be infinite. So let's see this. So is this point making sense? So even if you apply certain rules, and after that also your language can still be infinite, right? So let's see this language L3. Can you list down some of the strings in this language? Let's see this language L4 first. Let's see this language L4 first. Set of all strings starting with B over sigma equals to AB. Set of all strings starting with B over sigma equals to AB. Can you tell me? Can you list some of the strings in this language? Can you list some of the strings in this language? Okay, okay. Some more, Vasudha, maybe? Okay, great, great. I think both of you are correct. Why did you both miss single B? Is single B a part of this language or not? Can you guys tell me? Is single B a part of this language or not? Can you guys tell me? Yes. So you missed that point, right? Single B is a part of this language. BA is a part of this language. BB is a part of this language. B, anything, maybe 3-letter words, maybe BAA, BAB, BBB, and then BBA. And go and so on. This is an infinite language. Even if I have applied certain rules, even then my language can be an infinite language. This example was to motivate this point. So your language can be finite or infinite. There is no such rule which says that language always have to be an infinite one or a finite one. It can be finite also or it can be infinite also, right? Is it making sense? Yes. Now, can you tell me set of all strings of length n? So when I say length n over sigma equals to AB, this n is a constant. This n is a constant. Can you tell me, is this a finite language or an infinite language? Is L3 a finite language or an infinite language? Can you guys tell me? Is L3 a finite language or an infinite language? Infinite? When I am saying n is a constant, how can it be infinite? Vasudha, are you getting my point? It can't be infinite, right? So for example, if I keep this n as 2, you got some 4 strings. If I keep this n as 3, you got some 8 strings. And I am saying that I am keeping this n as a constant. Exactly. So that is why I said it's a constant, right? N is a constant. I'm not saying n is varying from 0 to n. I'm saying n is a constant. Then it becomes finite. So can you both tell me how many strings will be there in L3? Can you tell me the cardinality of L3? What is mod of L3? What is the cardinality of L3? So that means that the number of elements in L3, cardinality. What is the number of elements in L3? Can you tell me this? Number of elements in L3 given n is a constant. Is the question clear to both of you? I'll give you 1 minute to solve this. What will be the cardinality? Let me set the timer too. What will be the cardinality of L3? Tools, timer. So you have some 1 minute to solve this problem. Good, good, good. Isaki, you are correct. What about you? Vasudha, what should be the answer? Great, great. I think both of you are correct. So I hope you applied permutations and combinations concept to solve this. And it's a very, very simple question. That is why I gave you 1 minute only. See, you have some n spaces to fill. 1, 2, 3, 4, up to n. And at every place you can put, n, 1 out of the n characters that are possible. So let's say NC1, NC1. So out of the n, you will choose 1, right? So out of the 2, out of the 2 you will choose 1. So you should write it as 2C1, 2C1, right? Not NC1. Sorry for the typo. It is 2C1. Out of the 2 characters, you will choose 1. Out of the 2 alphabet symbols that you have, you will choose 1 out of that. So you will have 2C1, 2C1, 2C1. All are being getting multiplied by the multiplication rule of the permutations and combinations. You will have 2C1. So how many 2C1s you will have? N 2C1s you will have, which are being multiplied. So you will get something known as 2 raised to power n. Right? Making sense? We'll get something as 2 raised to power n. Now let us say I do not tell you the length of sigma. So can you tell me, okay, so I am not telling you, so let me give you a better problem. So let us say I do not tell you the length of sigma. I say that the length of sigma, I should say the cardinality of sigma, is mod of sigma. So mod of sigma represents the number of elements in sigma, right? Now can you tell me number of elements, number of strings in, number of n length strings over sigma. Now can you tell me n length strings over sigma? What will that be number? What number will be? So since you do not have mathematical operations to write, maybe you can write it in English. What will be that number? I hope as far as I see, YouTube doesn't allow you to write mathematical things, but you can write it some notation or English language. So the alphabet of the YouTube chat does not involve sigma. So that's what I'm trying to say, if we talk about in the terms of theory of computation. So I got some answer from Isaki. He says it is mod of sigma raised to power. Why we are getting this number? Same way. So you have some n places, 1, 2, 3, 4, 5, up to n places. At every place you can put mod sigma symbols. Out of mod sigma symbols, you have to choose 1. Mod sigma C1, mod sigma C2, C1, mod sigma C1, and up to n. So how many mod sigmas? Raised to power n. Is it making sense? Yes? Great. Now let's move to, so now we have understood the terminology of theory of computation. We will have strings. So first of all, we'll have some, what do we say, symbols. From symbols, we'll have some finite. So let us talk about all of them in one go. Like for example, let me take you back. I think there is, I'll take an empty slide wherein I'll try to summarize all these points. Let's see. So what we saw is we have symbols. So it can be any symbol. And after that, we understood the finite set of symbols which I have in my language is basically alphabet, and it is represented by sigma, and this is basically a finite thing. This is basically a finite thing. Now, from alphabets, I made strings. Strings are always going to be finite. You cannot have an infinite string. If you have to tell me something is a string, it has to be finite. How can it be infinite? Right? Strings are always finite. But then I move to something known as language. When I say strings are finite, I am not saying that number of strings are finite. I am saying that every string's length will be finite. Are you getting this point? There is a very, very subtle difference in this point. When I say there are two things, every string is finite, means it has a finite length. Otherwise, if it is an infinite length, how will I write that string? But number of strings are infinite. Is it making sense? Is this point making sense? Every string is finite, but number of string, every string is finite, but number of strings are infinite. Right? Yes or no? So if I am writing a string, it has to be a finite one, but number of strings that I can write is infinite. If I write a string of length 1 crore, I can write 1 crore one length string. I can go till infinity, but every string which I write on paper, it has to be a finite string, right? Now, when I say language, it is basically, when I am saying about a language, it is basically we are trying to say we have bound the strings that are there in the language out of the infinite strings that are there. I am bounding, I am putting some rule on them. That rule can make these number of strings infinite also. That rule can make the number of strings can be finite also. So therefore, the language can be finite also as well as infinite. I have given you the examples of both the types of languages. I hope this point is clear. Right? So now let's talk about the powers of sigma. Right? So when I say sigma raised to power n, sigma raised to power 1, this basically means strings of length 1. Let us say my sigma is a comma b. So in this case, my strings of length 1 will be single a and single b. Now let's talk about sigma raised to power 2. What is sigma raised to power 2? This is strings of length 2. This is strings of length 2. Exactly. Very good, Isaki. So what will it contain? We discussed earlier. AA, AB, BA and BB. Similarly, this means length 3. Right? This means strings of length 3. So all the 8 strings. So we'll have 8 strings over here. So we will have some 8 strings over here. Right? So now when I say sigma to the power 0, what does that mean? It's quite interesting thing. What is sigma to the power 0? What is sigma to the power 0? That is basically an empty string. How is it represented? What is the keyword for that? This is basically strings of length 0. Strings of length 0. How is it represented? How is it represented? Epsilon. Sigma to the power 0 means epsilon. Strings of length 0. So this epsilon is a special character which represents the absence of a string. 0 characters, 0 alphabets, like 0 combination of the alphabets have been used to form such strings. So this is basically epsilon. Right? Now what is, now before we go further, can any one of you tell me, what is the difference between epsilon versus phi? This is epsilon versus null. Can you tell me the difference between these two? Can you tell me the difference between these two? Okay, so empty. Isaki says one is empty string, other is empty set. Good. Now, what is the difference? So when I say empty set, what does that mean? And when I say empty string, what is the difference? Like, I got your point. One is empty string, one is empty set. But what does it exactly mean? So I gave you one jargon. In answer, you gave me another jargon. But what exactly it is, you have to tell me. Exactly. So just to answer, so what you are saying, Isaki, is 110% correct, but let me say it in a better way, right? So this represents, epsilon is going to represent empty strings. Right? And this, as you said rightly, this is an empty set. So basically, to represent that a language is empty, I will use phi. Right? An empty language will not have even epsilon in it. When I say a language L is phi, that means it does not even contain epsilon. This language L is an empty language. Right? So when I say set, Isaki, what I wanted to know from you is, can you give me an example of a set also? So language is a set. String is not a set. String is a combination of strings. To represent an empty string, I am using epsilon, and to represent an empty language or an empty set, I am going to use phi. Right? So phi represents not even a single string is there, not even an empty string is there. But a language may contain, a language may be just epsilon. This language is not empty. So, okay, I think this is not visible. I think it's visible, yeah. So this language is not empty language. This language has epsilon in it. When I say a language is empty, it means it does not even contain any string of length 0, 1, 2, 3, 4, anything, nothing is there. But when I say L is equals to epsilon, it means at least length 0 strings are there. So that is the basic subtle difference between epsilon versus phi. Is it making sense to both of you? Yes. So I think Isaki, you told it correctly, but I just wanted to say it in better words. Right? Is it fine, both of you? Can you confirm? Great. So now let's talk about sigma star. Let's talk about sigma star. Sigma star. Okay. I think it's not visible. Right? So what is sigma star? Sigma star is the union of sigma to the power 0, union sigma to the power 1, union sigma to the power 2, union sigma to the power 3 up to sigma to the power n. You take n as any number. N can go up to infinity, or I should say up to infinity. You can just simply write it as, just don't write anything, up to infinity it will go, right? We can write it like this, right? So when I say this, so it will have, for example, my sigma in this case is a comma b, my sigma in this case is a comma b. So it will have, this will have epsilon, this will have a comma b, this will have a b, b, union, and so on and so forth, right? Right? So this way, can you guys tell me, is sigma star going to be a finite thing or an infinite thing? It itself is going till infinity, it has to be a infinite one, right? It has to be an infinite one. So what is sigma star? It is actually all the strings that can be formed using sigma. So whatever string that you are going to make, whether it is a 0 length string, or it is a 1 length string, or it is a 2 length string, or it is a 3 length string, any string you talk about, right? Any string you talk about, that will be all the strings that can be formed using sigma will be your sigma star. And that is why it is called as the universal languages. This is called as universal language. Or the mother of all languages. Mother of all languages. Is it making sense? So this is, so for example, given a sigma, you cannot produce anything outside sigma star. This is what is the maximum limit, right? Is it making sense to both of you? Yes? Great. So now, just to motivate you further, just to give you a better picture, I should say, see, this is your sigma star. This is your world. Outside, if you use sigma, using sigma, you can produce, say, sigma star. So these are the strings, all the strings in sigma star are represented using this box. So any other language that you make over sigma, can you guys tell me, is going to be a subset of this? Because this is everything that I can produce using sigma. Any other language that I write using sigma will be a subset of this language or not? Can you guys tell me this or not? Can you guys confirm me? It will be a subset or not? Any damn language I give you, will it be a subset or not? Tell me. Yes? So for example, let's say this is my L, which is sigma star. L1, which I said, strings of length 2, strings of length say 2, right? L2 is, let's say, strings of length 3, right? Let's say L3 is basically strings starting with A, right, which is an infinite language also. So all these, L1 will be somewhere over here, L2 will be somewhere over here, L3 will be strings of length 3, 2, or maybe something like this. Undo. L3 will be something this. But all of them will be part of sigma star. They will never go beyond sigma star. Is it making sense or not? Yes? Yes or no? So all of them will be part of sigma star only, and that is why I told that sigma star is the mother of all languages. It is the universal language. Yes or no? Is it clear? They can also be infinite. Very, very good question. Right? Very good question. A subset of an infinite language can also be infinite. There is no issue. Right? We will see it as a theorem also in future, but a subset of an infinite thing can also be infinite. You are perfectly fine in saying this. So for example, sigma star is infinite, L3 is also infinite here. Right? Is it okay? A subset of an infinite language can also be infinite. And the example is there in front of you. Sigma star is infinite and L3 is also infinite. It is a subset of sigma star. Right? So what we tried to do is, we tried to understand in this session, what we did is we understood what is theory of computation. When I say theory of computation, what does it mean? It means modeling the computer systems. Then I saw the applications of theory of computation. Then we saw the applications of theory of computation, and one of the most important applications, we saw almost 6 to 7 applications. One of the most important is to accept or reject a language, right? And the compiler design is also a direct application of theory of computation we saw. And then we saw that to understand the capability of a machine or for verification, we use theory of computation. And any system, any digital device, any computing device that you see, you can model its behavior using a computer, using theory of computation, using the models that we make in theory of computation. And that model is called automata. And then we understood the various terminologies that are used, for example, the symbols, the alphabet, the strings, and then the language, right? This is what we have understood. And then we saw what are the various powers of sigma to the power 0, 1, 2, 3, 4 up to infinity. It can go till infinity to make sigma star. The union of all of them is called as sigma star, right? So this is what is basically the basic primary introduction of theory of computation. What we will do in the next session is, we will study about the deterministic finite automata in the next session. We will start making the automata ourselves. We'll do some ample amount of examples in the next few sessions. We'll do somewhere around almost, in every session. So let me show you the schedule, how we are going to go further. So let me take you directly to the schedule. So this is done today. We have given the basic introduction to the subject of theory of computation, right? So once the introduction has been done, what we will do in the next 3 sessions. So these 3 sessions are planned in the next week. So these 3 sessions are planned somewhere in the next week. That is Tuesday, Wednesday and Thursday. Tuesday, Wednesday and Thursday. We will be taking 3 sessions in the next week to study in detail deterministic finite state automata. So what I will try to do in this session is, cover at least 20 to 25 DFAs in the class so that you become comfortable in designing the DFAs. And we'll understand in detail the concept of DFAs in the next 3 sessions, right? Then after that, we have 3 more sessions after that. In the week of 30th May, on Tuesday, we will talk about minimization of DFA. 31st May and 1st June, that is Wednesday and Thursday, in that week we will be talking about NFA and epsilon NFA. So we will understand in detail, when we had DFAs, why we made the life complex by making NFAs, or did it make our life simple? We will discuss this question in detail. What was the motivation of bringing back the NFAs after DFAs? And then we'll understand the motivation of bringing back epsilon NFAs. When we already have NFAs, why the hell we made epsilon NFAs? We'll see what is their importance, and we'll also design a few of the NFAs also, and epsilon NFAs too, right? So once we do that, in the last week, in the last 3 sessions on 6th, 7th and 8th of June, I will be talking about regular expressions. We'll spend almost 2 lectures on regular expressions. We'll see it is one of the most important topics with respect to the GATE exam. And then in the end, in the last session, we'll check whether the given language is regular or not. So what are regular languages? These are the languages which are accepted by the finite automata. So given any language, can we tell that whether the given language is regular or not? We will see all this in the last session. So in these 10 sessions, we will lay down. So as I told in the beginning also, these sessions are foundation sessions to set up the foundation for all of you for the course, right? And after attending these sessions, you will be able to attempt all the PYQs that are there, all the previous year GATE questions that are based on these topics. And for advanced topics, you need to study further, like for example, the push-down automata or the linear bounded automata or the the Turing machines. These are all advanced topics which you can build up upon, based upon after building your basics and foundations on these topics, right? So so that's what it is. And just to make you guys clear, in the last GATE 2023 examination, we had 1 question from DFAs and 1 question was there from regular expressions too, right? So almost 2 to 3 questions, I guess. I think NFAs, no question was there from NFAs. Yes. So out of these 10 lectures, if you see the topic wise, we had at least 2 questions from this, all this what we did. So almost in theory of computation, we had some 5 questions. 2 questions were there from whatever the topics that we are covering, right? For the advanced topics, you need to study further and to understand them in a better way. But we will discuss all the basic topics which will help you in understanding the things further, right? So after attending these lectures, you can attempt all the PYQs based on these topics, and then you need to study further the advanced topics and then attempt their PYQs too, right? I hope this session was interesting for all of you. You could understand the motivation of the subject, the terminology of the subject. We'll start with deterministic finite state automata in the next session, right? I'll see you guys on the next Tuesday, coming Tuesday on 23rd of May with deterministic finite state automata. Sorry, just a second, the previous slide. yeah, so on 23rd of May, I'll see you with deterministic finite state automata. Yeah, okay. So see you guys. Thank you so much.